Good morning, Australia, Asia. Good afternoon, Europe. And good evening, North America, South America. We are frontier of big data, AI, and analytics. Our aim is unleashing ideas and insights for harnessing the successful future of business and society. I'm Tomohiro Ando at Melbourne Business School. This event is co-organized with Professor Robert Cohn at University of New South Wales Business School and Professor Valentin Zelenyuk, School of Economics, University of Queensland. Before we introduce Professor Rudin, here's a housekeeping. The structure of this event consists of 30 minutes of roughly 30 minutes presentation and discussion Q&A follows. Anytime, if you have any question, please submit your questions by using Q&A function. And if you want to learn this question, please upvote other question by using upvote button. Now, I want to introduce Professor Rudin. As we can see, the title is pretty long, but it tells us a lot. And we can see some keywords, machine learning, and high-stakes decisions. And Professor Rudin will explain more. So briefly, machine learning is a kind of subset of artificial intelligence based on the idea that systems can learn from data. A system with machine learning sometimes makes decisions automatically, or sometimes assists humans' decision by providing some inputs. And high-stake decision, it's kind of a decision, type of decision. It consists of existence of catastrophic loss as a consequence of decision. And cost of recovering that decision is pretty large, sometimes impossible to recover. And we are very delighted to learn these topics from Professor Rudin. Before Professor Rudin starts, I want to introduce her real briefly. After Professor Rudin completed PhD from Princeton University, she held positions at MIT, Columbia, and NYU. Now, Cynthia is a professor of computer science, electrical and computer engineering and statistical science at Duke University, and directs the prediction analytics labs. And she's also an associate director of the Statistical and Applied Mathematical Sciences Institute. Cynthia is a 3-time winner of the Inform's Innovative Applications in Analytics Award. She was named as one of the top 40 under 40 by Poets and Quants in 2015 and was named by BusinessInsider.com as one of the 12 most impressive professors at MIT in 2015. She has given keynote and invited talks at many conferences. Today, we are very pleased to welcome Professor Cynthia Rudin. Now, I'd like to hand over to Cynthia.
Thanks, Tomohiro. Okay, let me share my screen. Great, okay. I'm delighted to pretend to be in Australia right now. I would love to be in Australia. Okay. So yeah, I'm a machine learning researcher. I'm a computer scientist, and my talk is about the fact that I don't think we should use black box machine learning models for high stakes decisions. In fact, I don't think we should use them at all. Like, a lot of people are using them and explaining them, and I think we should simply not use them. Okay, so I want you to think about whether a typographical error could lead to years of extra prison time. Like, is that possible? Really? And the answer is yes, and it's actually happened. So this is a New York Times article about a guy called Glenn Rodriguez, who was in prison since he was a child for a crime, that he committed as a child. He was a model prisoner, and he came up for parole, and his parole was denied. And as it turns out, it was denied because of a miscalculated COMPAS score. So COMPAS is a black box model. It's a proprietary model that's made by a company that's used across the US justice system. And he only figured this out because he took his score sheet that was used with all of his data on it, and he compared it to someone else's after his parole was denied. And he realized that there was a typographical error in his criminal history features. So in fact, a judge did not make this decision, a typo made this decision. Okay, so what is a black box model? It is a formula that's either too complicated for any human to understand, or it is proprietary. And in the case of machine learning, these models are designed from databases, and those databases are not perfect, right? This is very different than if you're driving a car and you trust your car to do good computations, because that's a deterministic computation, whereas machine learning models are based on data that's random. Whereas an interpretable machine learning model is a constrained model. It obeys some kind of domain-specific set of constraints so that humans can better understand how it works. A human can understand what the computation is to see whether it's correct and whether it's depending on the right factors and so on. And there's a spectrum of interpretable models. You can have models that are very constrained so that a human can understand how everything is working. And then there are models that are sort of loosely constrained so that maybe like the model just increases along one variable, for instance. And why do we need interpretable machine learning models? We need them for high stakes decisions or troubleshooting. Like you need them when you really don't want something to go wrong, like for criminal justice models or credit scoring models, air pollution models. I've done a lot of work on like power grid reliability models, and anything where you really don't want it to go wrong and you really want a human to be able to check the computation. Okay, so what happens when we use a black box machine learning model for a high stakes decision? Well, bad things happen. So I already showed you an example of a typographical error making a decision, but also here's another example where if you were living in California during the wildfires in 2018, you might have used Google's daily air quality index to determine whether it was safe to go outside. But unfortunately, Google had replaced the Environmental Protection Agency's Interpretable model with a proprietary model from the company Breezometer. And that model was saying it was safe to go outside on days when there was a layer of ash on people's cars. So it really could have done quite a lot of damage, right, to tell people it was safe to go outside when it actually wasn't. So I hope not too many children went outside during those days. So that's an example where a proprietary model could have caused a real serious problem. Here's another one where a hospital algorithm was racially biased because it was using cost as the outcome, and the Black patients were receiving lower cost healthcare, and so the algorithm didn't think they were as sick, and so it didn't recommend extra care for them that it did for the white patients that were that had the more expensive healthcare. And that would have been something that would have been very easy to detect if the model were interpretable or transparent. And this is just the tip of the iceberg. I mean, probably a lot of things have gone wrong that I don't know about because they were hidden, but there's a lot of things that have gone wrong and could go wrong with these black box models. Now, I want to go back to COMPAS because I think this is a really interesting example because it's so widely used across the justice system that there's a lot of information about it online. So, so I mentioned that this algorithm is widely used, and the question that I want to know is how accurate is this algorithm, right? You'd think that a proprietary algorithm that uses maybe 130 some factors would be really accurate, right? A company designed it, they had lots and lots of data to design it. You'd think it'd be really accurate. Well, a couple of years ago, some data became public with COMPAS scores and some information about the people that were being scored. And so we could use that to figure out how accurate COMPAS was in comparison to standard machine learning methods and our own own machine learning methods from our own lab. So when this data came out, I took the data from Compass and we applied our latest machine learning method in the lab at the time. It was called Corals. We have more modern methods since then. But Corals is a method that produces really tiny itty bitty rule lists, which are sort of like made of if-then rules, just a model that's made of if-then rules. So we took the data, we put it into this algorithm, and we told it, give us a predictive model for whether someone will be arrested within 2 years of their Compass score calculation. And the model that we got out was so tiny that I can put it on the bottom of a PowerPoint slide, okay? So I'm gonna show you, I'm gonna put the whole machine learning model right on the bottom of this slide, okay? So here's the model. It says, if you are 19 to 20 years old and male, predict arrest within 2 years of your Compass score calculation. Else, if you're a little bit older, like 20, 21 or 22 years old, and you have 2 to 3 prior offenses, then predict arrest within 2 years of your Compass score calculation. Or if you have more than 3 prior offenses, then predict arrest within 2 years. Otherwise, predict no arrest. And we looked at this model and we thought, there is no way this model can be as accurate as Compass, right? This super complicated, like proprietary model. There's no way these two things can be equally accurate. But as we found out, they actually are. So what I'm showing you here is a plot of this is accuracy for both Compass and Corals, and the different colors are different subsets of the data. So typically machine learning researchers break the data into several pieces, and they train their model on 9 of the pieces and test it on the 10th piece. And then they rotate which fold is the test fold. So what I'm showing you are different subsets of the data, and you can see that these algorithms are really about equally accurate. So we were like, whoa, this is crazy. What happens if we try out lots of machine learning methods, like our black box machine learning methods, super complicated, combinations of the variables? Let's see what happens. And as it turns out, no matter what we did, we couldn't improve the accuracy over either Compass or Corals. And these models are the state-of-the-art machine learning models. This is boosted decision trees, if you're familiar with that. This is support vector machines with radial basis function kernels. This is random forest. And so what I'm showing you here is that even if you apply these super fancy black box machine learning methods to this problem, you're just not going to increase the accuracy anymore. And there's good reasons for why you wouldn't be able to increase it more, because there's a lot of randomness as to whether or not somebody will be rearrested within 2 years, right? So anyway, we were wondering, okay, something, the justice system is using Compass, and there was a big fuss over fairness of Compass, algorithmic fairness of Compass. But the truth is, we don't seem to need Compass at all, right? So why are we still using it? I'm not advocating that we should use the Corals model, right? There's obviously flaws with that model, but there's no reason for us to be using Compass. Okay, so far I've just talked about interpretable machine learning, which is when you use a model that is not a black box, okay? Like the Corals model that I just showed you, you could understand exactly how the variables were working together to form the prediction. But I want to contrast that with explainable machine learning, which is really popular right now. This is like all the craze at the moment, which is when you take a black box and you try to explain it afterward. So you take the data, you throw it into a machine learning algorithm, and you get some sort of super complicated formula that you can't understand. And then you try to figure out what that formula is doing. So you would start with a black box, and then you either create a model that approximates it, or you compute derivatives of it, or you visualize what part of the input the model's paying attention to. You basically do something to excuse the fact that you're using a black box model. You make excuses for it. Now the problem is that many people, including most machine learning researchers, I would say, do not understand that these two things are completely different from each other, and that there's a there's a chasm between these two things. So I'm gonna just go through a few reasons why explanations of black box models are not the same thing as designing inherently interpretable models. Because like I was telling you for the corals model, what a lot of machine learning researchers would do is they would just throw a black box at it, and then they would try to explain what that black box is doing. They would never use something like corals, right, to get the little itty bitty model that I just showed you. Okay, so one reason why we don't, why explanations of black box models can be faulty is this issue that I call double trouble. Double trouble is where you have to rely on two models instead of one. You have the black box and you have the explanation model. These are two models. And those models necessarily disagree with each other. They have to disagree with each other, because if they don't disagree with each other, they're always the same. And then in that case, you can throw out the black box model and just use the explanation model as an interpretable model. Okay, so they have to disagree with each other. And then the question is how often? Now, some people show explanations and they say, well, this explanation is right 90% of the time. But what that means is that 10% of the time it's wrong, which means 10% of the time you can't trust the explanation, which means 10% of the time you can't trust the black box. So you're still in trouble there. The problem with typographical errors does not go away if you explain a black box model. If you go to the trouble of entering a ton of information about Glenn Rodriguez into this complicated form, that problem is still going to be there whether or not you've explained the black box model. And also, if you can produce an interpretable model that's equally accurate, why should you explain a black box? That doesn't make any sense to me. So again, it doesn't make sense to me why we are using Compass when we could use a model that's as simple as the corals model that I just showed you. You know, maybe the explanation is an excuse for improper data analysis. You know, the fact that you don't go to the trouble of creating a model that's inherently interpretable. And maybe we are actually using black boxes when we don't need to. Now, another issue that we have in machine learning is that our terminology is kind of messed up. So a lot of people think that making an approximation of a model is an explanation of what that model is doing. But it's not, it's just an approximation. It just produces the same predictions. It doesn't necessarily rely on the same variables. So I'll give you an example. So let's say that this is a representation, like an abstract representation of our black box predictive model. And I come up with another model which approximates it. That is, it's a simpler model that approximates it, okay? But these two models depend on different variables. They're about equal to each other, especially right around here. Maybe that's where you want to make an explanation. But the explanation model depends on age, priors, and race, okay? Whereas the black box, let's say it only depends on age and number of priors. So what could happen is that you created your black box, you didn't know what it depends on, and so then when you create the approximation, you say, this approximation depends on race. That means the black box also depends on race. And therefore, it's a racist model and we shouldn't use it. Now, the problem is, you'd think nobody would make this mistake because it seems so obvious, right? It seems so obvious that people wouldn't make this mistake, but actually people have made that mistake. And they made it with Compass. And in particular, there was a group of reporters, journalists that took Compass scores. They took Compass scores, and they approximated Compass with a linear approximation model that depended on age, priors, and race. And then they declared that, in fact, this means that Compass depends on race in addition to age and priors, which are correlated with race. So that article that I'm telling you about was actually a very famous article by the group ProPublica. And yeah, so they specifically, the whole article was framed around the fact that Compass depends on race. So I want to go, and yeah, this is exactly what they did. They approximated Compass with a linear model, declared then that because the linear model depended on race, then Compass depends on race. Okay, so let me give you a little bit more detail about what ProPublica did, because it's actually really interesting. So they showed that the false positive rate and false negative rate of Compass depends on race. Okay, they showed that, or sorry, that it not depends on, that it varied by race, because you're seeing different statistics for different races. And so then they realized that, oh wait, this might not be a good comparison, because the people in Broward County, Florida, where they got the data from, they had different statistics because of systemic racism in society. They, the Black people in the database were younger and they had more prior crimes in their history, whereas the white people were older and they had less priors. And so they said, okay, hold on, we need to take into account age and number of priors, and we need to recompute, compute this, right? We need to take into account age and number of priors. So they included age and number of priors and created this linear model, linear approximation to compass, with a low p-value for the race covariate, which means that according to this linear model, compass depends on race, or this approximation depends on race. And so they then declared that that compass depends on race. But as I was telling you, the approximation, I don't think the approximation is right. I don't think compass is linear. And so their conclusion that compass depended on race actually didn't follow from their analysis. So I want to give you a little bit more detail on why I think compass doesn't necessarily follow a linear model. And so I'm going to use the same data set that ProPublica used. This is this Broward County, Florida data. And what I'm plotting here is the compass violence score as a function of age. Okay, so age, right? And what I'm seeing, I don't know if you can see it, but there is this sharp lower bound right here. Like somebody who's 20 is not going to get a score that's like -4. It's just not going to happen, right? There are a few outliers in our analysis. I think maybe those were people whose score was calculated wrong or something like that. But the vast majority of, it's lots and lots of people here lie above this interesting curve here. And that curve is not a linear function of age. You cannot draw lines here. It's just not a single line, okay? It's a curve or a piecewise linear function, but it is not a line. And in fact, a line would be particularly bad at younger ages, which is where a lot of the data are. So yeah, I don't think a linear approximation is necessarily the right thing to do here. I actually think this might be compass's the contribution of age to compass. I think we actually might have uncovered a bit of the proprietary model in this analysis. Okay, so then we were still curious, well, does compass actually depend on race, right? Is it possible that it does? So what we did was we took the compass scores and took out this interesting function, which we call f of age, which we think characterizes compass's dependence on age. We took that out. And then we did an analysis where we did machine learning with and without race and tried to approximate compass scores, and it didn't really matter whether we included race or not. We got almost the same accuracy. So yeah, we ran machine learning methods with and without race to see if we need race to predict compass well, and they perform similarly. Okay, so then it makes you wonder, like, how did ProPublica end up with all these pairs of individuals where it's like one Black, one white person, where the Black person is high risk with a low criminal history, and the white person has a much bigger criminal history, but a low score? So how do you explain that, right? Because it really seems like compass depends on race. Well, the first thing you want to notice is that these people are very different ages. So this guy who's older doesn't get the age points that she does. And I'm not saying I'm not saying I think that's a good thing. I'm not saying I think it's fair. I'm just saying they didn't take into account the dependence on age when they showed these pairs. But also there's another factor that goes into looking at these data and looking at these pairs, which is that there's something about using complicated proprietary models that's makes me kind of concerned, which is that their data are compass surveys. So it's 137 factors entered by hand for each compass survey. Now, if somebody makes like a typographical error in 1 in every 100 things they're entering, so 1% error rate on a survey, that leads to at least a 75% chance of at least one typo on a survey, because you're entering 137 factors by hand in the survey. So what that means is that these surveys could potentially be chock full of typos. And so I claim this is a serious disadvantage to complicated or proprietary models that goes above and beyond being able to, it's just it's just for anybody who's affected by the justice system, they're subjected to the problem of these typos. It's a kind of universal issue. And so, yeah, the problem that I mentioned with Glenn Rodriguez, it doesn't just happen to him. It actually happens quite a lot. And people have emailed me and told me it happened to them. Anyway, we were wondering how often it happens in Florida. So we found a bunch of individuals in the database who had really interesting COMPAS score criminal history combinations. So these are a bunch of people who have COMPAS score of 1. So this is the lowest possible COMPAS decile score. So this means low risk. And these people have significant criminal histories. You can see here are some of their prior charges, including things like attempted murder in the first degree and attempted robbery with a deadly weapon and so on. And these people have the lowest possible COMPAS score. So I can't think of how else this could possibly have arisen aside from a typographical error. This is only the tip of the iceberg. We found a lot of people like this. So these are people with COMPAS scores of 2 and 3 and 4. These are very low COMPAS scores, right? The highest score is 10 for the deciles. And yeah, these people have serious criminal histories going on here. And then we even found typographical errors in the COMPAS documentation. So the company that makes COMPAS is called Northpoint, and they actually claim that their model is linear in age. They claim that it's a linear function of age. I don't think it is. I think that they should have had that it was some other function of age in the score. So anyway, we wrote this paper about it, and there was commentary from 5 criminologists, and actually Northpoint actually wrote a response to our article, kind of blasting the analysis, but they admitted, and you're welcome to read that because they didn't blast it very hard, and they actually admitted that they all but admitted that we were right. They said that they do transform the variables before they put them in, so it sort of justifies what they did. And we wrote a rejoinder and everything. It's really interesting conversation if you want to read it. Anyway, so going back to interpretability versus explainability, I'm putting up a picture from DARPA's Explainable AI BAA. And this was supposed to show that there's a trade-off between accuracy and interpretability. So it's supposed to show that if you have high learning performance, you can't know what's going on. Whereas if you have, if you really know what's going on, you have low learning performance. And I looked at this figure and I was like, whoa, there's something wrong with this figure. First of all, there's no problem that this corresponds to. There's no data involved in this. This looks like somebody created it with a Sharpie. Yeah, so then I thought, well, okay, let's just buy it for now, okay? It looks like they're talking about working with a static data set, so just a fixed data set, and you run a bunch of different machine learning methods on it using a fixed evaluation metric, and you're supposed to see, a dot for each algorithm or something. But that's not the way we do data science, right? Data science is a process where you are supposed to, create the data, create the evaluation metric, run your machine learning, evaluate what's going on afterward, like interpret, what's going on afterward, get some insight, use that insight to refine your data set and refine your evaluation metric. And so in that case, interpretability actually gives you accuracy at the next round. It actually makes you better because you know what you're doing. So this plot doesn't take that into account. And then also, even if you ran with a single data set using a fixed evaluation metric like accuracy or something, the trade-off doesn't happen like this. This is just not the way it happens. It's usually just flat. And I showed you an example earlier. In fact, I showed you the COMPAS example where I tried many different machine learning methods on the same data set and got the same learning performance. And I tried black box models and interpretable models, and they all perform the same. And that happens for, to be honest, a lot of data sets, in fact, most data sets. Anyway, it also didn't, this plot also didn't talk about whether they were explaining black boxes or building inherently interpretable models. And as it turns out, they were just explaining black boxes. So I finally, I got so sick of this that I finally wrote a paper that just told people, look, you really shouldn't do this. This is really not safe. So I originally titled the paper, "Please Stop Explaining Black Box Models," but the editor made me take out the please. So now it's a little bit more commanding, like, just stop doing this. Anyway, so the reasons that I gave are the same reasons that I told you a few minutes ago. So for instance, the fact that these black box models lead to typos, which cause problems in practice, and no amount of explaining a black box is going to solve that. Black box models still force you to trust a data set because, and I've never met a large data set that wasn't messy. These large data sets have so many problems with them: systemic biases, typos, all kinds of weird stuff in them, medical data sets, the way doctors interact with insurance is all embedded in these data sets. They're very, very messy. There's this other problem I mentioned, double trouble, which forces you to rely on two models, the black box and the explanation. They have to be different. And if you can't trust the explanation, you can't trust the black box. I also talked about the fact that explanations are not really explaining what's going on because they don't use the same variables. And I specifically talked about the ProPublica scandal, where they said that Compass depends on age, criminal history, and race, but their analysis is wrong. It probably only depends on race through its correlations with age and criminal history, which those correlations, as I mentioned, are there because of systemic racism in society. And then I think the most powerful reason against black box models is that if you can produce an interpretable model, why should you explain a black box, right? Do you really want to extend the authority of the black box, or might you consider trying to actually use some interpretable machine learning tools and replacing those black boxes with models that people can understand and use and trust? Okay, so thank you very much.
Thank you, Cynthia. Yeah, it's a very insightful talk, and I have a number of questions. And I want to ask audience, if you have any question, please use Q&A button and post question. And there's a time allocated for Q&A. And in the meantime, I want to start conversation with Cynthia. So your talk tells us a lot. And typically because traditionally, for example, in business, I'm at business school. For example, in finance, asset pricing, we use some factor models, and PCA is sort of machine learning. And when we use machine learning and PCA, we extract some factors. Then by using this factor, we try to explain asset return. But in the end, a client, if we are managing funds, a client would ask, what are you doing? It's very hard to explain. And there are so many areas we are suffering this type of machine learning's kind of black box. And I really appreciate your insightful talk and giving us a kind of caution. We should be very careful around this area. And so I want to move on to a bit more. So this talk is about high stakes decisions, typically. So there's a variety of high stakes decisions. Typically, a business again, for example, some high stakes decisions are under time pressure. Also, some high stakes decisions should be made with incomplete data. As we can, if we have a huge budget, huge amount of time, we can collect whole information. But the reality is, budget is limited, human resources is limited, and time is limited. Under this circumstance, we have to make a decision, and it's some time. And your talk one of the values to stakeholder is explainability, and this is my understanding. And in your talk, can you please clarify a bit more about what kind of high stakes decisions are within this scope? And what kind of high-stake decisions are outside of your talk? Can you elaborate a bit more?
Yeah, I mean, what I can't do is give you every possible high stakes decision, but I can name a few high stakes decisions that don't need interpretability. So one of them is in radiology. So let's say that, so I work now with a radiologist, and we're working in mammography. And there are multiple types of decisions that doctors make. So one type of decision is whether or not there is a lesion in an image, right? Is there a lesion? Like, is there something to investigate in this image? Is there some strange, you know, is there a lesion in the breast, right? And if there is no lesion, the only explanation the AI can give is simply there's no lesion. So you can use a black box in that case. There's no explanation you could possibly give that would even be helpful. But if the doctor has to decide whether or not you need a biopsy, that decision takes the doctors a while to figure out. That's a much more complicated decision. And if it goes wrong, it could lead to lots and lots of people getting extra biopsies, so lots of extra surgery that people don't need. And we don't want that to happen. And so there's a whole way people have to think about lesions that we want to take into account. I'm realizing, based on the first question, that I might need to look at some of the extra slides I brought with me, because this person is asking. Yeah. Yeah, it's a good question. So she says, when a black box model outperforms an interpretable model, should we, what are your suggestions? Should we try to extract features from the black box model? What's your perspective about the SHAP value? So I've never used SHAP values in my life, but I'm going to tell you why I haven't, and I need a couple of slides to do that. So I hope that's okay. Is that okay with you, Tom?
Yeah, please.
All right. So I'm going to go back to sharing my slides again. And there's a few slides here, but this is a subtlety that you're asking about. It's really important. So there's really two types of data in machine learning problems. There's tabular data, which looks kind of like that. And there's raw data, which is like image data or text data, or like sound signals or something like that, where these two types of data function really differently from each other. Like for the raw data, you really need a neural network, because it's the only technique that's working right now in this data. And those are typically considered to be black box models. Whereas for tabular data, like I showed you with the COMPASS model, all with minor preprocessing, all the methods have similar performance, right? I showed you that with the Florida data. So for these tabular data, you're not getting any benefit from these neural networks or any kind of complicated models. And so you can use like super sparse, like little itty bitty decision trees, like the corals model I showed you, and you won't lose accuracy over the black boxes. So the question really is about the raw data, about like neural networks. And this is where people are using things like SHAP values or like, Lime or something like that. And the thing is that you can actually design, oh, sorry, I forgot to mention something. With raw data, the definition of interpretability changes. Like you would never use a sparse decision tree on pixels. It just doesn't, it's not interpretable. It doesn't make any sense. So because, the type of data, the raw data is a very different structure to it. Like, for instance, if you're talking about images and you take an image that lives on the natural image manifold, like a natural image, and you change one pixel, then it's no longer on the natural image manifold. So anyway, you have to define interpretability really carefully for raw data. You can't define it the same way. And so we've been actually defining interpretability differently for these two domains. So here it's sparsity, and then here we have definitions that are designed for computer vision. And so you can actually design an interpretable neural network so that you don't need to use something like SHAP or Line, because the whole model is inherently interpretable. So like the kind of models we're designing, they look kind of like this. This is one example where the neural network would take a look at this bird and say, well, I think this is a clay-colored sparrow because this part of the bird looks like this part of that bird, and this is a prototypical clay-colored sparrow. And this part of the bird looks like that part of this bird, and this is a prototypical clay-colored sparrow. And so the network is actually doing all these comparisons, and it's telling you sort of not only where it's looking in the image, it's telling you what it's doing with that information. It's not just giving you attention, right? Attention is this stuff. That doesn't tell you what the network is doing. This tells you what it's doing. It's saying, I think this looks like that. And there's an actual number that the network provides for how similar it thinks this looks to that. Yeah, so this network has been used in a couple of different medical applications. It's actually a fairly simple technique. It adds a prototype layer to any black box neural network, so that you take your favorite convolutional neural network and you add an extra layer to it that makes the network do these prototype comparisons. I don't want to go into too much detail here, but it actually, for every comparison the network is making to another image, it actually produces a number. And so the human can decide whether or not it believes that the network is reasoning about the image properly. And what we found when using this network is that it actually achieves accuracies that are within the same range as the black boxes that we started from. And when you combine a whole bunch of these interpretable networks together, you actually get an accuracy that's better than any of the black boxes we started from. So we're not losing any accuracy over the black boxes, which is why we don't ever need to use Lime and Chap. And so we've been applying this to mammography, as I mentioned. So you take the lesion, and then the algorithm says, well, I think this part of the lesion, like the borders of the lesion, look like this part of this lesion, and this is a circumscribed lesion, and so I'm going to give it some points for that information. And so yeah, so we haven't ever found a reason to use Chap or Lime, because those are basically a cop-out for not designing the algorithm properly in the first place.
Thank you for explaining that. Yeah, if you have any question, please post your question by using Q&A button, and Cynthia will answer. Yeah, so let me go back to the question. So in the talk, you mentioned about typo of database. And my understanding is even this can happen, even we use interpretable machine learning or even standard statistical procedure. And how can we avoid, or how can we handle this typo when we use standard statistical procedure or interpretable machine learning? Because in the end, we are using the same database with typos. And how can we handle that in practice?
So there's no 100%, there's no way to handle it with 100% certainty, but if you only have like 5 factors in the model, it's just much easier to check 5 factors than it is to check 137 factors.
Yeah. And yeah, because, oh, I see. The assumption is basically based on the domain knowledge, we shrink the number of variables we can use, you can input into the model. By using this subset of variables, we can check manually. Is that what you are suggesting?
Well, I mean, the idea is you just build a model that has fewer variables involved in it. So for instance, if you want to build a decision tree, it would ask you a series of questions, and it would take you down one side of the decision tree. And let's say the decision tree was only depth 5, right? If it's a depth 5 decision tree, everybody gets 5 questions. They can be different depending on your earlier answers, but only 5 questions. Or if you want to design a little scoring system, like you get 3 points for this, 2 points for that, 1 point for this, then you only have to check, the number of things in the scoring system. You generally wouldn't pick the features based on domain knowledge, although that you could. You would generally try to get the machine learning method to produce a sparse model for you. And yeah, the field we've been developing sparse models for years and years, so we have some very good algorithms for designing sparse models.
Yeah, thank you. Yeah, so let me come back to the interpretable model a bit more. And the benefit of my understanding is because we can interpret the result, and there's a transparency. And in addition to that, any benefit to users for decision making? And the question is, when we use interpretable models, explainability, and it's a kind of clear these things. On top of that, any other benefit for users, decision maker, when we use interpretable models instead of black box models?
Yeah, so yeah, I'm busy writing this paper actively. I spent a good chunk of the day writing a paper about embryology with a bunch of IVF doctors, um, and you know, it was actually we were writing. We have a whole giant list of things that
Oh,
interpretable models help with. But I think the bottom line is that you know if you're using a black box model, the decision is being made by the model. If you're using an interpretable model, the decision is being made by the human. So, because since the human can't understand what the black box model is doing, either the human has to just go with it or not. And so, if you go with it, the decision is made by the black box, right? So it actually these black box models take the human out of the decision making process. And so for things like in vitro fertilization, it really causes problems because now it's like, okay, if something goes wrong, who's responsible? Is it the human or the black box? If it's the black box, is it the company who made the black box that's responsible, or is it the doctor because this is the doctor's patient? And then also you have issues where the doctor can't, if the doctor knows something, if they have some extra information about the patient, there's no way they can incorporate that into the model. You also can't tell whether the doctor also can't tell whether the model is using some like information it's not supposed to use. Like, what if it's using information about the machine that is measuring everything? Because since the doctor can't understand what the model is doing, the model could be using this information that's really not supposed to use. And especially with image processing, it's really easy for these neural networks to use like all kinds of information. Like when we started working in mammography, the networks were using healthy tissue to make predictions about like healthy tissue over here to make predictions about a lesion over here. Like it wasn't even looking at the lesion. It was just looking at all this other stuff over here that was helping it make a prediction. And yeah, that's not what it was supposed to do. And so since we knew that the network was misbehaving, we knew not to trust it for that particular decision. So yeah, there's a lot that can really go wrong with if you use black boxes. Yeah, I mean, also for self-driving cars, like let's say the car crashes, and you know that it was the computer vision system that it was at fault, right? Because the control part is easy. It's the vision system that's really complicated. But you don't know what went wrong, right? Car crashes into a human, and you have no interpretability. You don't know why, so you can't fix it. You don't know. You honestly don't know what happened. So it's really useful, even though the algorithm is driving the car, right? To actually have interpretability as to what the algorithm's doing, so you can troubleshoot it, figure out who's responsible, figure out what happened. Yeah, so does that make sense?
yeah, I agree. It's a very important issue. Even self-driving car, when accident happen, who is responsible? That's the kind of open question. Even at this moment, I have no clue around this area. But yeah, some at certain point of time, we as a society we have to decide, clarify many things. But still, the testing self-driving car is ongoing, and yeah, that's a very important theme. Thank you for sharing your thoughts around this area. And yeah, so on top of that, because you are often referred to kind of medical science, my understanding in that area is we are talking about human body, right? And because the degree of uncertainty, we are probably the machine learning a neural network, these things are talking about the variation, statistical variation. It's not about uncertainty. Uncertainty is kind of structural change. And so my understanding of machine learning and these things are pretty good at dealing with variation, statistical variation. I mean, if the mean is 3.5, even 1 year later, mean still sits 3.5. The issue of uncertainty is this mean 3.5, for example, gonna change to 5 or something like this. It's a kind of idea of uncertainty. The parameter value gonna change. And let me come back to medical science, because the human body structure is pretty much kind of stable, long time. And I mean, genome sequence, of course, there are some mutations, but still, it's nearly the same. If one medicine for headache is effective 100 years ago, still it may be effective even now. My prediction is even maybe 100 years later. I'm not talking about the virus, but just chemical functionality. So in that sense, human body is pretty much stable. It means that the degree of uncertainty is pretty low compared with other kind of phenomena like stock market. The structure changes, investor sentiment changes, and many things are going on. Regulation changes, it creates changes of the investor's behavior and so on. And under a fair amount of uncertainty, let's say, and how black box models and interpretable models can accommodate this uncertainty. And that's the kind of question I do have these days. Any thoughts, opinion?
I'm not sure I completely understood the question, but you know, machine learning models make predictions for individual people in individual circumstances, right? They make very, very specific predictions. So they, you know, they do try to make these, you know, very fine-grained predictions. There are ways to estimate uncertainty bands. The classical way of getting uncertainty bands is like bootstrapping, where you change the training data set and recompute models all the time. And then you look at the range of predictions for all of those models at a specific point. There also is, there's a new technique called hacking intervals, which are a type of robust confidence interval, where they look at all the machine learning models that predict the data reasonably well, and they look at the range of outcomes associated with all of those models. So, you know, so in other words, the prediction from any good model will be within a hacking interval. And so you'll get an uncertainty band that way.
I see. So, yeah, so it's kind of measuring the kind of variation of the data set, right? So let's bring it a bit more accurately. COVID, now it's still ongoing. Because of COVID, consumers' behavior changed a lot. Used to be less spending on online, although the online market is expanding. The presence of online is emerging now. Like this, if we build a model based on what you suggested, and then bootstrap, then before COVID, it is effective. But the uncertainty COVID plays in. Then how effective this bootstrap confidence interval or something, and that's the question. So yeah, what's your thought?
This is a major problem in machine learning, domain adaptation, where you use the model in a different domain than what it was trained. And when you do that, you cause issues, lots and lots of issues, and things break, which is another reason why interpretability is super useful, because you can look at the model and you can go, oh, wait, I really shouldn't be using this model in this circumstance because it's wrong. So we're writing a paper right now about lending decisions. And, you know, a person who was reliable up until COVID, and then their business dried up during COVID, and they want a loan, that's very different than a person who has been irresponsible before COVID, right? They're very different circumstances. And so that would affect your lending decisions. But if you didn't know what the model was based on, it might just sort of say that this person who's actually reliable is actually not reliable anymore, and their loan application would get denied. Yeah, domain adaptation is a real problem. Also, another example is the in vitro fertilization example that I was talking about, where, you know, the company develops the model on a set of very specific reagents, you know, with very specific equipment. And if you are a doctor and you don't have those reagents and you don't have that, your model might not work. And you might not know about it if it's a black box.
Yeah, thank you. So the point is, because once uncertainty comes in, the previous data set, the value of historical data is diminished extensively. And in the end, my feeling is our gut experience plays a lot. And but the question is, we are using machine within the organization, for example, we are using machine learning long time. And what will be the trigger point? Shifting from, now let's assume that every day, not every week, or for example, we are using machine learning, interpretive machine learning. But however, for some reason, we have to shift to humans' decision completely. And what will be the trigger point? This forces us to make this shift, relying on this interpretive machine learning heavily towards to human decision significantly. What will be the trigger point? Any advice to us?
Well, I mean, the machine learning is just capturing what it's patterns that it sees in the data. So, and humans have a different way of thinking, a systemic way of thinking. We could think about problems from many different angles and many different perspectives. And so you can measure how accurate the machine learning model is over time. And when it starts slipping, or when the factors that are important for the machine learning model start to be less dependable, that's when you want to start thinking, maybe I'm not sure I want to use this model. And then, if you're a really careful human, you can keep track of your own accuracy and see how that changes over time as well. Yeah, I'd love it if you could keep track of how well you and the centaur of you and the machine combined is doing, and then pick the best out of the three going forward.
That's also a good idea. Keep track the accuracy. Then sudden shock happen, the accuracy gonna diminish. Then it's kind of signal saying, oh, that's a good idea. Yeah, that's right. So also I have another question. Sorry, too many questions I do have. Because for some domains, to explain some event, there are a lot of variables. Maybe, let's say, 100 variables are playing to explain some phenomena. In that case, it's very hard to human to understand. Probably. Are there any way to use interpretive models to deal with this high-dimensional problem? Because
definitely. So it depends what the domain is. So for example, for computer vision, each pixel is a different dimension. So you have hundreds or thousands of dimensions there. And we're using case-based reasoning, like I showed you on those extra slides. But there are other ways to do it too. So you can create models that are decomposable. For instance, let's say you work in lending and you want to create a model that uses a whole bunch of variables. What you can do is divide those variables into groups and make smaller models for each of those groups. So these are called subscales typically. And there are special machine learning tools that create very sparse models for each of the subscales. And then you can say, okay, this is the delinquency subscale. This is how many points the person's getting for delinquency. All right, this is the balance and the trades subscale. This is how many points the person's getting for that. And so then you take these 100 variables that then divide them into like 10 subscale models. Those subscale models then get combined into like another model. So there's always ways that you can create constraints to make the model sort of more interpretable for every domain that I've ever worked in and I've ever heard of. There are some domains where I simply don't know what's going on because I don't know the domain, but even in super weird domains, like I started working in material science recently, and in material science, you can look at a material and be like, I have no intuition about what's going on at all, like none. But even there, we've been able to find models that we can understand. Yeah.
I see. Yeah, so that's great idea. Categorize variables so that users can interpret. Oh, that's good. That's good. Yeah. So to avoid So then I want to ask something more. Audience, oh, there's no question. So to avoid non-positive consequence by using kind of AI and machine learning, for example, some prison and hiring, etc. What kind of aspects should we or society or business and also academia should be mindful? Any advice to us?
Well, for parole and bail decisions, right, these are high stakes decisions that affect people's lives. And so those, and there's also been a lot of studies on recidivism, and there is no reason to believe that you need a black box model for those problems. So for those problems, even tiny little predictive models are as good as the black box ones, like I showed you an example with Compass, but we've also done other studies on much bigger data sets, and other people have done them too. And there's really no need for black box models in those particular problems. For, let's see, what was the other type of domain that you mentioned?
Business.
Business. Oh, hiring. You said hiring.
Oh, yes. This is an ongoing issue because quite often, because historical data set, quite often it contains bias compared with the ideal state. And so because data set is biased, let's say.
Yeah, every data set is biased.
Yeah, and how can we diminish bias through building the machine learning, or how can we diminish the bias from the historical data? And how can we move on to the future?
Yeah, so there's a whole field of algorithmic fairness right now where they're adding extra constraints to try to make the algorithms less biased. Well, it's really differently biased. You're not going to remove bias. You're going to make them differently biased. But you can. So one thing you should know though about bias, the bias constraints, particularly the racial bias constraints, is that they behave very differently than interpretability constraints in practice. So interpretability constraints we can add without losing accuracy. But racial bias constraints, they cannot be added without losing accuracy most of the time, because if you have different races having different statistics, like different whole underlying populations, then when you try to improve accuracy on one population, you have to reduce accuracy on the other. And that's just the way it is. Because these two constraints can't be satisfied at the same time, like make it accurate and make it fair. The constraints simply conflict with each other. And so the people working on algorithmic bias have a much more, in some sense, a much more difficult job to do than I do, because there's no way they can actually get their constraints to work and keep their accuracy.
Yeah, so then what would be the ideal outcome in that situation? Any thought?
Yeah, so we have a paper on algorithmic fairness and criminal risk scoring. And we actually went through a whole bunch of different fairness metrics and evaluated a whole bunch of risk scores with respect to them. You know, I think the one thing that's pretty clear is that there's no single metric of fairness. There's a whole bunch of different metrics, and you have to decide for your problem which one is the one that you actually want. And that is, you know, that's the same thing with interpretability, right? You have to pick which interpretability metric you want. But I think the fairness metrics are they're very contentious. Some people have a lot of disagreement about what the right fairness metrics are. So that makes it kind of difficult for the algorithmic fairness people.
Yeah, thank you. I just want to ask a bit more about lending problem. What would be the challenge you had when you are analyzing data by using machine learning? What would be the point we should be mindful when we analyze such kind of data? Any thoughts?
So we participated in the FICO Explainable
Oh,
Machine Learning
okay.
Challenge a couple of years ago, and they handed us a beautiful data set, and they said, create a black box and explain it. That was the rules of the competition.
Oh,
Okay, so they give us data for lending, well, it was lending decisions, and it was like 10,000 people they gave us, their whole, features about their credit history and so on. And they said, yeah, that was the rules of the competition. Create a black box and explain it,
black
and we'll
box
judge you
is
on
a
the quality data.
restriction? Black
Yeah,
box is a restriction. Okay. Yeah,
what?
yeah. Yeah,
Yeah, that
black
was
box.
the object. Yeah,
Okay.
create a black
Yeah,
box. So we didn't do it. We took the data and we created an interpretable model that had the same level of accuracy as the best
oh,
neural network that we could construct on the data set. Yeah, we didn't have any trouble with it with that particular data set. We did it in I think we had only like a month or two to build everything. We built a beautiful visualization tool so you could see the model. It was really fun. I think the issues with financial data, there's a lot of political issues. Like there are companies who control these models. They want the models to be black box. They want them to be proprietary because it's their secret sauce, right? Your credit score. If I tell you these companies tell you, oh, your credit score went up, you should go check it, right? Go check your credit score. And then sometimes they give you these reasons that don't make any sense why your credit score went up or down. Like, I think, at some point I paid off a loan and I got these two contradictory things from my credit scoring company. Like it said, good job, you don't owe money to a lot of creditors, so you get some more points for that. And then it said, oh no, sorry, it was the other way around. It was like, you don't owe a lot of money to people. And then it was like, oh, but you don't owe enough money to enough people. And so you're losing points for that. And I was like, why don't you just tell me how the damn thing's calculated? Because then I know what, if I wanted to raise my credit score, what should I do? Should I borrow more or should I, what? So I was like, luckily I don't need you guys. I just paid off my loan, but still, it was it was pretty frustrating.
oh.
Yeah, so I think there's a lot of
Oh.
political issues with lending decisions.
It reminds me a lot. It reminds me a lot because sometimes the purpose of initially the black box model is improve prediction accuracy, let's say, for example. That was a starting point. But in business, let's say, for example, sometimes using black box model, using itself is the purpose and the starting point. And sometimes interpretability and prediction accuracy, etc., is forgot. And it's a very important point to us. Yeah, it's very important. So we have a question from Richard. Aside from simplicity, do you have any other recommendations for those who are trying to build their own decision trees instead of black boxes?
Well, okay, so the thing is that, I'm a machine learning researcher at a university. So, how do I say this? I mean, so I've just written a review paper on interpretable machine learning, but I don't know how accessible it would be for people who are outside of machine learning itself. So I guess my advice is get a data scientist and tell them to use an interpretable machine learning technique if you want to avoid a black box. And try to get somebody who's trained to be able to learn new things, because right now all the training, unfortunately, is just teaching people neural networks. And so it's the first thing people try, and they don't even try anything else. And it's really sad that this happened, because when I was being trained, you were learning decision trees, you were learning, you were learning all different things, but now we are literally only teaching people neural networks, so that's all they know. But I'm gonna just grab this review paper real quick and just pop it in the
Yes, please.
Pop it in the chat. Here we go. Yeah, so we just wrote this. It's in draft form. Let's see, I can't. Oh, panelists and attendees. Okay, great. So that is the link. And the paper, it's called Interpretable Machine Learning, Fundamental Principles and 10 Grand Challenges. And so it gives you an overview of the whole field, but like I said, it's pretty technical. Yeah, I'm gonna just I'll just type in the title here. There we go. Yeah.
Yeah.
So apologize that it's not for a general audience, but you know, these are very mathematical.
Yeah, thank you. Yeah, associating with that, because this is what quite often this happen, because the starting point is we use AI, machine learning. That's the starting point within the organization. And even data scientists thinks, oh, as you suggested, Cynthia, oh, simple model is enough. We don't have to use machine learning or AI because simple model is enough. I fully agree. Quite often.
Hold on, you're building these simple models with machine learning techniques, though.
Yeah,
you're not just whipping them off the top of your head. You're using machine learning AI to do it.
Yeah, thank you. So the point is, quite often, the starting point is we have to use black box model. That's a top down, right? So even the data scientists within the organization, they probably don't have enough control. Even manager may not have enough control. Instead of using black box model, we're gonna use interpretable model. And because if they were asked use black box model, neural network, how can they explain to their boss, this is better? Any advice? It's a kind of realistic
question.
That's an
easy one. That's an easy one. So the first thing you do is you run a whole bunch of black box machine learning methods. You run random forests, you run boosted decision trees, you run neural networks. You run those 3 techniques, and you get numbers for those. And then you run several interpretable machine learning techniques. And let's say that you run something or other. Let's say you run corals, or you run you know, our latest decision tree method called generalized optimal sparse decision trees of GHOST. So let's say you run GHOST and you get a little tiny decision tree, and you find that it's just as accurate as the black box. Then you bring it to your boss and you're like, hey, I ran all these experiments, and what I found is that this interpretable model performs as well as these black box models. So maybe we should think about going with an interpretable model.
Yeah, that's a great idea. Yeah. So if a simple model is enough, that's great. The issue is if the assumption is, okay, the performance of interpretable model and black box model, these are similar, the performance, let's say the metric. So if the black box model outperforms interpretable model, how can we convince? Sorry, at the next level question.
Yeah, so at that point, you know, it's possible, but the truth is with tabular data, I haven't seen that much. If you're willing to, you know, if you do pre-processing correctly and you use an interpretable modeling technique, I generally don't see that much loss in accuracy. And we've seen no loss in accuracy with the interpretable neural networks. So yeah, I mean, if you're finding a gap, it probably means you didn't pre-process your data correctly, or you didn't use the right algorithm, or you didn't use it right, or something like that. That's generally the case.
I see.
And if you really can't figure it out, then it would be a surprise. It's a surprise to me in that case, because like I've worked in so many different domains. I've worked in power grid reliability, a million different medical fields. You know, like just I've worked in all kinds of different problems, material science. I've worked in NASCAR racing. I worked with police officers. I'm at criminal justice. I'm all over the board. And I've never seen a problem where I needed a black box.
Oh, really?
So, I mean, I just showed you a bunch of computer vision examples where we were using the benchmark data sets where the deepest of the deep neural networks are trained, and we still found interpretable models the same level of accuracy as the black boxes. So I just haven't seen a problem like that where you really needed a black box.
Yeah, thank you. Because what you told me pleased me a lot. Because even from my experience, I was always wondering why I have to use kind of very complicated stuff. kind of interpretability is important, and explainability is also important. So the question, I was always wondering, because even the performance, as you said, is very similar, both interpretable machine learning and black box one, according to my experience as well. And I'm working on kind of financial data, kind of credit scoring, and many other domains, like consumers' behaviors. And yeah, so I agree with you. According to my experience as well, I didn't met extreme case like black box model outperformance significantly compared with interpretable machine learning model. And yeah, so far between us, yeah, we are on the same page. I don't know others. And any other question from the audience? No here. From here.
Well, I mean, so I personally think the greatest living machine learning experimentalist is Rich Caruana, and he doesn't even he gives this talk that's called "Friends Don't Let Friends Use Black Box Models," and even he says that he can use additive models for like raw medical records, which is crazy. I mean, he's throwing data in there that's literally just time series of people's medical records, just throwing into this additive model, and he's getting just as accurate as everything think of. So even he says, yeah, we don't need black box.
Yeah. So yeah, so yeah, it's very nice to learn. It's pleased me a lot. So thank you. Because the time is coming up, I want to ask the final question. If audience has no question. So yeah, from all the many interesting things covered today in your talk, what is the one sentence, bottom line advice or conclusion you would like to give to our audience, or re-emphasize again? Maybe you have 5 minutes or so.
I think it's scary if people want to make high stakes decisions with black box machine learning models. I think there's no reason to do that. And I think that it puts a lot of people at risk in these high stakes decisions. So I think they should stop doing that.
Okay, it's very simple. Yeah, it's very simple. Yes, so on top of that, I have a question about, because you're in academia, can you explain a bit more about the current trend on your field? Because we have some students, PhD students in our audience. Can you any advice to students? What is going on? Which field is emerging around this in your field? Can you please advise?
So yeah, sure. So the first bit of advice is that you need to realize that right now there's a ton of people who are working on explaining black boxes, and the reason they're doing that is because it's hot, and so you need to be careful about trying to choose things that are ethically okay research directions, and just be careful if you're going to work on explaining black boxes. So the other thing is that this link that I've sent you is a survey paper of 10 grand challenges in interpretable machine learning. I don't know if I can name them all off the top of my head without looking at the paper, but I'll cheat. There we go. Okay, so the first one is optimal sparse decision trees, which is kind of like the corals model I showed you. So these are optimal sort of logical models that use if-then rules. The second challenge is on optimization of scoring systems. Scoring systems are sparse linear models with integer coefficients. So this is like, you get 1 point for this, 2 points for that, 4 points for this, and those points add up to convert to some risk. And those are used very often in medicine and criminal justice. So the question is, how do you create those automatically from data? The third question is about generalized additive models, which I didn't talk about today. The fourth one is about case-based reasoning, including neural networks that do case-based reasoning, like the bird example that I showed you. The third one is about the fifth and the sixth ones are about disentanglement of neural networks, so that you take a neural network and you try to force information to flow in certain ways through the network so that you can better understand how the network is processing certain types of information. The seventh one is dimensionality reduction for data visualization. So this is where you take a high dimensional data set and you project it down to 2 dimensions and try to preserve all the structure in that data when you project it down to 2 dimensions. And sometimes you can see clusters or interesting manifolds in 2 dimensions after you projected it down so that a human can look at that data. The eighth one is machine learning models that incorporate physics. And that's mostly for like the physical sciences. And then the ninth one is about characterizing the set of almost optimal models called the Rashomon set. So these are models that are maybe not quite perfect, but they only have a little bit of error compared to the best one. And if you look at that set, you might kind of understand how, if you perturb something small, how the prediction might change, and understanding whether there are a lot of good models or if there are only just a few good models. And then the last one is on interpretable reinforcement learning, which is kind of mostly for like robotics, and the reinforcement learning is also for advertising and things like that. Okay, yeah, so that hopefully students will be interested in that.
So is that paper available through online?
Yeah, I put the link in the chat.
Oh, chat. Oh, thank you very much. Thank you. Yep. So any question from the audience? Probably not. Oh, here's one comment. Thank you very much for the great presentation. That's the comment.
Yeah.
Yep. So, yeah, that's it's okay. So, finally, this is the final question I have. So, what is your next couple years research agenda? If possible, can you share with us, please? Any?
Yeah. So I've been, I always try to challenge myself to try to find new domains where the definition of interpretability changes and where I don't really understand the domain very much. And so right now, those 2 domains are material science and mammography. So those are 2 domains that I'm really trying to pursue. Some of the ongoing projects in my lab. So the corals project I've been working on forever, like for my whole professional career. So I'm still working on that, and I have a collaborator who I've been working with for many years, and she and I have a whole team of students trying to construct decision trees. And then other projects, within the last year, I started doing a lot of work on dimension reduction so that we could take high dimensional data and project it down and try to figure out what's going on with it. So we have some new algorithms for that. And that is quite useful for biology, actually, for just trying to understand like cell populations and cell behaviors and things like that. Yeah, I think a lot of my research agenda ended up in that overview paper. A lot of the challenges in there are things that we're actively working on that we think are important.
Yeah, great. Thank you very much, Cynthia. Because time is coming up, so I want to wrap up. First of all, thank you very much, Cynthia. It's your insightful and very constructive advice to us. We really appreciate your advice. And also, thank you very much for joining us. Without your attendance, this event cannot happen. And thank you very much for joining us from Asia, Europe, and North America, South America. Thank you very much, and Australia as well. Our event series will continue, and when we have the next plan, we are now planning the next event, and please follow up with us, and we circulate our event flyer when it is ready. Again, thank you very much, Cynthia, today. And thank you very much for all. And we want to close the event. Thank you very much, everyone. See you next time. Bye.
Bye.
Bye.